Hello everyone, this is Sarthak, and this would be my first video on YouTube on a topic which is rarely touched upon by anyone. And also, it has very less content on YouTube or any other platform. So, the topic I would be covering in this video is quantum computing in finance. Before I start, let me tell you that each and every word I speak is based upon pure peer reviewed research papers, whose link I would give you in the description so you can verify it from by yourself. So, let's get started. So, finance has always had one major problem. Uncertainty creates an enormous amount of computation. So, you can think about what a modern financial institution has to do. It has to optimize portfolios. It also has to price derivatives, calculate risk, or detect fraud, analyze customer behavior, and it also has to constantly react to changing market conditions. And as the number of assets, scenarios, and constraints increases, these calculations become much harder. This is where quantum computing becomes interesting. So the idea is not that quantum computing simply do everything faster. The real idea is that for certain mathematical problems, they may use a fundamentally different way of computing. So in this video, let's go from the absolute basics to some of the most important applications of quantum computing in finance. So before understanding quantum computing, we need to understand the problem it is trying to solve. So for like example, let us start with portfolio optimization. Suppose I have hundreds or thousands of assets. I don't just want to choose which assets to buy. I also have constraints on position sizes, diversification, transaction costs, liquidity, and risk. So the number of possible combinations can become enormous. Now, take risk management. Financial institutions use stochastic simulation to ask questions like what happens to my portfolio under thousands or millions of possible future market conditions. And derivatives can even be more difficult because the payoff may depend on an entire path of future prices. So, this is why Monte Carlo simulation, optimization algorithms, and machine learning have become fundamental tools in quantitative finance. So the problem is that accuracy often means more computation. Quantum computing is attractive because several of these financial problems have a mathematical structures that map naturally to quantum algorithms. Now let's understand the basic difference. A classical computer works with bits. A bit is either a 0 or a 1. A quantum computer works using a qubit or a quantum bit. A qubit can be represented as a combination of the two basis states, alpha times 0 plus beta times 1. The important thing is that alpha and beta are probability amplitudes. When we measure the qubit, we eventually get a classical result. With multiple qubits, the state space grows very quickly. An n qubit system is described using amplitudes associated with up to 2 to the power n basis states. But there is an important point. Quantum advantage does not come simply from having many states. Quantum algorithms carefully manipulate those amplitudes using three key ideas: superposition, entanglement, and interference. This is what allows the algorithm to make some answers more likely and other answers less likely. So, how does this actually become a computation? A useful way to think about quantum algorithm is a five-step process. So the first step is we encode the problem into quantum states. Second, we create a superposition of possible states. Third, quantum gates transfer those states. Fourth, interference is used to increase the probability of useful solutions and suppress unwanted ones. And finally, we measure the system and get a classical output. So you can notice something important here. The quantum computer does not magically gives us any answer. So the measurement we get is probabilistic. The algorithm has now to be designed so that the solution we actually want has a high probability of appearing when we measure. This is the fundamental idea behind quantum algorithms. So till now I have covered the quantum algorithm basics. Now let us see how we can apply it to finance and solve some very important real life problems. Let's take probably the most intuitive example, portfolio optimization. The classical Markowitz problem asks us to balance two things, expected returns and risk. So mathematically, risk is related to the covariance matrix of asset returns. W transport sigma W, while expected return is W transport mu. In the real world, however, portfolio optimization is not just about these two terms. We also have minimum and maximum investment limits, transaction costs, liquidity constraints, and concentration rules. So, to use a quantum optimization method, we can transform the problem into a QBO, which stands for quadratic unconstrained binary optimization. Instead of directly asking whether an asset should receive a continuous weight, we can represent decisions using binary variables. For example, 0 could mean don't select a particular allocation level, and 1 could mean we select it. Then we build a single mathematical objective that rewards expected return, penalizes risk, and add penalties for violating constraints. The quantum system's jobs becomes find the low cost configuration. This is a much more natural problem for quantum optimization. So there are different quantum approaches to these optimization problems. One is quantum annealing, where the system is used to search an optimization landscape for a low energy solution. And the another one is QAUA, the quantum approximate optimization algorithm. It is a variational quantum algorithm specifically designed for combinatorial optimization. And the application go beyond static portfolios. For example, you can consider arbitrage. Suppose an asset or currency can be converted through several markets. You can represent assets as nodes in a graph and conversion opportunities as edges. The question becomes, can we find a cycle through this graph that generates the highest possible profit after accounting for conversion costs? That can also be reformulated as an optimization problem. So, till now, researchers have been tested dynamic trading trajectory problems where the goal is to optimize position across multiple time periods while considering transaction costs and market impact. Now we come to one of the most important applications, Monte Carlo simulation. Monte Carlo is everywhere in quantitative finance. We use it for derivative pricing, portfolio risk, and other problems where the future is represented probabilistically. So imagine that you want to estimate the average outcome of a complicated financial system. Classically, you generate many random scenarios and average the results. But the problem is the number of samples you need. The classical Monte Carlo estimation error scales approximately as 1 over the square root of m, where m is the number of samples. Quantum amplitude estimation, or QAE, can theoretically improve this scaling to approximate 1 over m. This is a quadratic improvement in the number of samples needed for a given accuracy. And this matters enormously in finance because a large number of simulations may be required before a result becomes precise enough for risk management or pricing. So, this creates an obvious application in derivatives and risk management. You can consider a path dependent derivative such as an Asian or Bermudan option. Its value depends on what happens across a sequence of possible future prices. Classically, this can require a huge number of simulations and calculations. Quantum amplitude estimation can potentially accelerate the estimation of quantities derived from those simulations. The same idea applies to risk. Value risk or VAR asks roughly how large could my loss be at a particular confidence level over a given time horizon. And conditional variance asks once we are beyond that threshold, what is the average loss? Because these calculations depend on probability distributions and repeated scenario evaluation, they are natural candidates for quantum acceleration. But remember, these are algorithmic possibilities. They do not mean today's quantum hardware can already outperform classical financial infrastructure in production. So, quantum computing is not always about optimization. Another major research area is quantum machine learning. Finance already uses machine learning for credit scoring, fraud detection, market analysis, and customer behavior. For example, in credit scoring, we may want to determine which combination of features best predicts whether a borrower will default or not. Or in fraud detection, we may want to determine whether a new transaction resembles previously detected fraudulent behavior. Quantum machine learning explores whether quantum circuits can make parts of this classification, regression, dimensionality reduction, or pattern recognition tasks more efficiently. One interesting example from literature is quantum feature selection. Instead of simply using every available feature, the selection problem itself can be formulated as a QBO, where the objective balance is predictive power against redundancy. So the quantum computing can potentially help both with the model and with the optimization problems surrounding the model. So now comes the most important reality check. Quantum computing is not just automatically better for finance. One of the biggest challenges, especially for quantum machine learning, is getting classical financial data into a quantum state efficiently. This is called data encoding. For example, with angle encoding, financial features can be mapped into rotation angles of qubits. But as the number of features grows, the encoding itself can become expensive. There is another problem, noise. Quantum states are extremely sensitive to their environment. Errors can accumulate, and quantum information can be lost through decoherence. This is why today's machines are generally described as NISQ devices, noisy intermediate scale quantum systems. We are not yet at the stage of large, fully faulty tolerant quantum computers. Instead, many practical approaches are hybrid. The quantum processor handles a specific subproblem, while a classical computer performs optimization, data processing, and other tasks. So, what could the financial system actually look like? It probably won't be a world where quantum computers replace every classical server. A much more realistic picture is a hybrid financial computing stack. Classical systems continue to handle databases, conventional analytics, execution, and most business processes. Quantum processors are called for specific computationally difficult tasks. Portfolio optimization could become more sophisticated. Risk engines could evaluate scenarios more efficiently. Derivative pricing could use quantum enhanced estimation. Machine learning workflows could potentially use quantum subroutines for certain difficult tasks. And this is why the most important question is not will quantum computers replace classical computers? The better question is which financial problems have a structure that makes them worth sending to a quantum processor. So basically, we would have to decide what task should be given to a classical computer and what task should be given to a quantum computer because it has a very higher edge over a classical computer. So where does this leaves us? Quantum computing in finance is promising, but it is not magic and it is not production ready for everything. Today, the field is largely in an experimental and hybrid stage. Researchers are exploring portfolio optimization, arbitrage risk, derivatives, credit scoring, fraud detection, and quantum machine learning. The most compelling theoretical advantage appears in problems involving optimization and probabilistic estimation, such as quantum amplitude estimation for Monte Carlo. But important challenges remain hardware noise, error correction, data loading, algorithm maturity, and proving an actual advantage over the best classical methods. So perhaps the most accurate way to think about quantum finance is this. It is not a replacement for classical finance. It is completely new computational tool that may eventually let us solve some financial problems that are currently too expensive, too slow, or simply too complex for classical computers to solve. And if that happens, the impact on finance could be enormous. So this is this is what quantum computing in finance is. So this is my complete video on quantum computing in finance. Thanks for watching. And before ending up, let me just introduce myself, who I am. So I am Sarthak Ashya, and I am currently a civil engineering student at IIT Bombay. I am currently in my third year, and I am looking at various topics such as quantum computing. I am also exploring finance. I am also involved in a civil engineering related project. So that would give me a broader area to cover in my next and future YouTube videos. So thank you, and if you like the video, you can press the like button, and you can subscribe me for better videos in the future. Thank you.